We're going to talk about the programming framework for the differential privacy library. And I'm thrilled to have today, we should all be thrilled to have today, Marco Gaboardi, who's professor of computer science at Boston University, and Michael Hay, who's a professor of computer science at Colgate University. Marco, it's all yours.
So actually, this is Michael. I'll start the talk, and then Marco will jump in the second half. Yeah, so we'll be presenting an overview of the framework. So this framework is described in a white paper that was co-authored with Salil, but we also wanted to acknowledge the valuable input we received from the other members of the design committee. So I think Salil already kind of covered the basic timeline. I'll just sort of highlight the end of it, which is that there is this white paper available on the OpenDP website. And we'd love you to look at that and give feedback. We also want to acknowledge that there's a lot of work that's been done in the community on building differentially private systems or designing languages for differentially private computation. And our design certainly borrows from this prior work, in particular Pink and Fuzz and Ectolo. But no doubt there's other ideas that are out there that are not yet incorporated into the framework. And so if you have suggestions or insights, we'd love to hear from you. And as a reminder, there's a breakout session tomorrow where we'll be discussing the framework. So these are the Desiderata that the design committee developed for the framework. There's many, I won't go through them all, but I did want to highlight the importance of modularity. So modularity is a useful feature in just about any software project, but I think it's really vital for this one. And so as actually Bryant alluded to in the previous talk, implementing DP algorithms can be quite tricky. It's easy to make mistakes. And so what you really want is that the core subroutines are implemented once, reviewed carefully, vetted closely, and if they're sort of don't appear to be vulnerable to any of the known attacks, then you take those components and you use them as widely as possible within your project. So certainly you want the code to be modular, but it's not just the code that you want to have where you want modularity. We also want the privacy statements to be expressed in a way that's modular and composable. So that way, ideally, it's possible to build, a complex differentially private program using library components, and yet, avoid at the end of it having to sit down and write a proof that the program you just built is differentially private. Ideally, that proof will sort of come with the library. And some of the other desiderata will be alluded to throughout the talk and in fact, throughout the workshop. So in the rest of the talk, we'll kind of do a technical dive into some of the components of the library, starting with measurements and transformations and building up to interactive measurements. And then we'll turn to some practical considerations, things like the implementation language and how people might use and contribute to the library. Okay. Just a few sort of assumptions to get started. These will be relaxed later, but for now, we'll think of the private data as just, a table of records or formally a multiset. Each item in the multiset is of some type X. And a person, will contribute at most one record to this data set. And our goal is to support the kind of pure DP, so epsilon differential privacy, but we'll talk about other variants later. Okay, so measurements and transformations. So starting with measurements. So a measurement is really essentially just a differentially private computation on the data. And in terms of the implementation of a measurement, we think of it as like an object, although we're not committed to object-oriented programming design per se. So an object or a struct that's defined by certain attributes. So concretely for a measurement, it has the following attributes. And as you'll see throughout the talk, like the set of attributes is gonna get larger and a little bit more complicated, but for now, a measurement, you define an input domain. So that is the type of data that the measurement is expecting to receive as input. The function, that's the randomized computation itself. And then the privacy loss, which is just the epsilon that would be spent when this measurement is invoked on the data. So here's a small example. So we have noisy sum, which takes as input a multi-set of bounded floating point numbers. So they're bounded to lie between L and U, where those are user specified parameters. And it computes the sum of these numbers, adds Laplace noise, and where the noise is appropriately scaled based on the parameters L and U and the desired privacy loss of epsilon. So one sort of detail to note here is that the privacy promise that comes with this measurement object is conditioned on the input type. So in particular, if you were to pass this measurement function a collection of unbounded floats, then you would not, this privacy loss of epsilon would not be guaranteed to hold. Okay, so those measurements. Transformations, these encapsulate all the things that you might do to your data to kind of prepare it for measurement. So filtering out rows or columns or applying user-defined functions to each element in the data set. And so conceptually, a transformation is a function that takes in a data set and produces a transformed data set. In terms of the implementation, it's defined by 4 attributes. So the type, data type, or the domain of the input and the output, the function itself, and then this stability parameter. And so stability is a promise that the transformation is making, which is that inputs that are similar, so say 2 inputs that differ by D records, that when you apply this transformation, you're going to get outputs that are also similar to each other. And so they can differ by at most C times D records, where C is this stability constant. So an example of a transformation is clamping. So you might take a data set, so clamping expects a data set of unbounded floats. And what it does is it applies a clamping operation to each float in the data set. So it will clamp the float so that it is guaranteed to lie between L and U. And it has a stability constant of 1. Okay, so measurements and transformations are the kind of core building blocks. And if the goal is to build complex differentially private programs from these building blocks, then to kind of continue the metaphor, we need the cement or the mortar that's gonna stick these building blocks together. And in this framework, this comes in the form of operations like chaining, composition, and post-processing. So I'll talk briefly about all 3, but I'll start with chaining. So chaining is the name that we use for function composition. It's just composition is kind of an overloaded word, so we wanted to have a specific term to distinguish it. But the basic idea is when you chain 2 operators, the output of one operator becomes the input for the next. So you can chain 2 transformations and that yields a new transformation. You can chain a measurement with a transformation that yields a new measurement. So concretely, this M prime is a measurement that consumes the transformed data set that was transformed by T. And so chaining as an operation is responsible for doing a few things. So you need to kind of check compatibility between the operators. So in particular, the output type of the first one should match the input type of the second one. But it also derives the privacy properties of the resulting operator that you're building. So if we kind of revisit the tools we have so far, we can consider chaining them together. So we can chain noisy sum and clamping, and what we get is a noisy clamped sum. So here the input is a multi-set of unbounded floats, but what the function now does is it clamps them and then computes the noisy sum of the clamp values. The privacy loss of this resulting transformation is C times epsilon, where C is the stability constant that you get from clamping, and epsilon is the privacy loss from the noisy sum. So that's chaining. Post-processing you can think of as a special form of chaining, where basically the idea is that you're passing the output of a measurement function to any arbitrary function you want, and it doesn't diminish the privacy guarantee. So another way of thinking about that is the sort of chained operation M prime enjoys the same privacy that the original base measurement M has. There's also composition, which is the idea of just taking multiple measurements. This comes in different flavors. So the simplest is sequential, where you're just taking multiple measurements. Of course, you can have adaptive measurements, where subsequent measurements are adaptively chosen based on the outputs that you receive from earlier measurements. So here, M2, you'll notice, takes as input Y, where Y is the output of M1. And so I'll defer the details about composition until later when we get into interactive measurements. But maybe one parenthetical remark I'll make here is that there is subtlety around using composition primitives because they actually behave somewhat differently depending on which variant of differential privacy you are using. And so we want a framework that can support different variants of differential privacy and use the appropriate composition tools for them. I'll skip this example, but really the take-home message here is just using the tools we've already introduced of noisy sum and clamping, we can also compute noisy counts as well as averages. And in the white paper, we have more in-depth examples, such as fitting a linear model using gradient descent. So in a minute, I'll hand it over to Marco, who will continue a discussion of kind of the components of the library. But I want to pause here and talk sort of briefly about verification. So what do we want? Well, we want that all of these transformations and measurements that are going to exist in the library, or that can be built from components of the library, we want these transformations and measurements to be valid. And by that, I mean that the measurement or transformation respects the privacy loss or the stability bound, which is promised by the attributes associated with that measurement or transformation. And so what we need to verify are these functions which are constructing the measurements or transformations. So functions like make noisy sum or chaining, those require a proof. And so, that proof should say things like, for all inputs that we supply to this function, either it'll raise an exception because you've supplied bad inputs and sort of the operation you're trying to do doesn't make sense, or what it'll output is a valid measurement or transformation object. I think we need to make other statements like it shouldn't modify any operators that were passed in as inputs or do any other weird things like modify other parts of the library code. These proofs can be supplied by a contributor to the OpenDP library and then verified and vetted by OpenDP, or they could be derived automatically. And we believe that if a function's built out of library components like existing measurements and transformations, and they're combined with the chaining and composition tools I described earlier, it seems possible that we should be able to verify automatically the privacy properties of these kind of constructed measurements and transformations. And this is where an implementation language can really help because we can, by providing things like strong types and immutable structures. Okay, so I'm going to turn it over to Marco. So he's going to take what I've just described, which is kind of the library as restricted to pure DP on multi-sets of records, and introduce enhanced functionality in the framework that makes it possible, that makes it more flexible and extensible to richer data types, but also other variants of differential privacy. So let me stop sharing my screen. Marco, you can take it from here. Great.
Right. Thank you, Michael. Hi, everybody. I'm Marco Gaboardi. So as Michael was saying, the next step that we want to present is how we want to generalize the basic framework that he just presented. So it's natural to think about generalizing it because we want to, for concrete application, we want to deal with different data types, not only multi-sets. We want to deal with intermediate data representation. Some examples are table, graph, stream for input data types. We may want internal vector or tensor representation. So we need to generalize the framework that we have so far. And here is an example of how we can try, for instance, to generalize. We can relax the need for the input to a measurement to be a multiset, and we can allow a single float so that we can rewrite the noisy sum function that we saw before as a chaining of a bounded sum, which still depend on the input L and U, and the base Laplace function, which just add the noise. We want to support this kind of generalization. We want to make sure that the different component have the right type, so that we make sure that we combine all the objects that match the right type. And to do this, we enhance the design we presented before by adding some metrics to measurement and transformation. In particular, we add input metric to the measurement attributes and input and output metric to transformation attributes. We don't need to add output metric to measurement because for the notion of privacy we don't in general need the metric on the underlying space. So as an example, we can have now a data type for the output metric of bundled sum or the input metric of base Laplace, which is on float, and the natural metric is the difference in absolute value. Now, chaining will work as before, but it will also check that the input metric of a measurement matches the output metric of a transformation, and that the type in general match. We also generalize the notion of privacy loss from a privacy loss to a privacy relation. The reason why we need the privacy relation is because we want to address a different notion of privacy. For instance, we want to capture approximate differential privacy, rendered differential privacy, or concentrated differential privacy, which are all relaxation of the standard notion of differential privacy. And to do this, a single privacy loss parameter is not enough, because we need, for instance, for approximate differential privacy, both a value of epsilon and delta. And usually there is not only one value of epsilon and delta which we may choose, and so we want to relax to relations. So in particular, if we build again on the measurement structure we had before, now the privacy loss turn into a privacy relation. So in particular, let's see this as with an example. If we want to introduce a Gaussian component, a Gaussian mechanism, like a standard in approximate differential privacy, we can define a relation which is the usual relation that we need between epsilon and delta for this mechanism. And also we add an output measure which describe that we are using approximate differential privacy. In other component like Laplace, we may want to use a standard differential privacy, or we can use a different privacy relation with another output measure like Rényi differential privacy. A similar generalization can go into transformation. So we can generalize from a single stability component to a stability relation. The stability relation allows us to have more flexibility on the kind of transformation that we can implement. For example, we can implement join, bounded join as a transformation by using a relation which allow different possible value of stability. Now, because of this generalization, we also need to generalize chaining and composition. And now the interesting part is that chaining and composition can use this relation on the components to derive the relation of the chain transformation or measurement. So here, I show an example of the generalization of chaining of a measurement with a transformation. And what happened is that to check the privacy relation of the component of the compose measurement, we need to check the stability relation of the transformation and the privacy relation of the underlying measurement. So these kind of privacy calculus or privacy relation calculus and stability relation calculus can be done through chaining and composition. Another way we need to generalize is to address not only static measurement, but also interactive measurement. So what is an interactive measurement? The way we structure it, what we want is something that to which we can ask multiple queries in an interactive way. And the way we think about structuring it is an interactive measurement is something that creates a queryable object, and we think about queryable object as a state machine consisting of an initial state and an evaluation function which evaluate the query and evolve the state. So in particular, the interactive measurement has attributes which are similar to the one we described before for basic measurement, but in addition, it also has it creates a queryable which is composed by a state and an evaluation function. This may be more clear through an example, which showed how we can use this queryable to answer actually queries. So an example is a form of, the example I want to show you is a form of adaptive composition. And here I didn't show you all the possible code, and the code don't need to be taken as set in stone. It's just an example of how we could write such a interactive measurement. So the interesting part here is the evaluation function, which take a query, which is a measurement and the state, and return an updated state and the result of the query. And the way this is implemented, we check mainly that the privacy loss of the query is less than the epsilon that is in the state, so that we know that we can perform the query. If we pass this test, then we return the result of the query and we decrease the privacy loss. Now that we introduce interactive measurement, we need also to generalize chaining, post-processing, and composition. So for chaining, more or less, the situation is similar to the one we had before. Now, the interesting part is that with post-processing, we can assume that the function f that before was just post-processing the result of the measurement, and now need to post-process a queryable, and what the function can do is to produce a new queryable. So in this way, we can use a function to create, to combine different kind of post-process analysis on the queryable. Some example of these, for instance, if we want to implement a gradient descent procedure, we can define this as a post-process of a composition like the one we saw before. Another thing that we need to generalize is composition. And here we have a different alternative on the kind of composition we can have for interactive measurement. I show you how to use interactive measurement to design a kind of adaptive composition, but we may want to have a more general form of compositions. And two forms that one may want are a sequential composition, where maybe all of the queries in the first inner queryable must be completed before another inner queryable is generated, and concurrent composition, where we have multiple inner queryable that can run in parallel. So these are things that have been already done in the differential privacy literature, at least some of them. But what we want is a general framework, a general design that can support all of them. So with this, I conclude the first part on what are the different library components, but let me, and I hope we gave you a bit the feeling that the library look for flexibility and modularity, but let me go also in some practical considerations. So first, the library, what provided by design is the idea that we produce only valid measurement and transformation. As Michael said before, we wanted that everything that is built out of the library come with an automated privacy proof, or anything that is added to the library come with a proof. And of course, this is an important part of our design. But in addition, we will need also to prevent other leakages, like leakages created by timing channel, by implementation of arithmetic, for instance, on floating point number, and by use of pseudo-randomness. These are some of the privacy leakage that have been exploited in the differential privacy literature. So the way we think about addressing timing channel is by using standard mitigation that have been designed, and by use specific mitigation for components that are based on user-defined function. For implementation for the arithmetic part, we plan to use as much as possible fixed point number and integer arithmetics. And to address a randomness problem, we plan to use a cryptographic strength pseudo-random generator. In addition, in order to guarantee, to ensure really the privacy, as Michael already hinted before, we will try to use as much as possible feature from the implementation language. And some desired feature that we have are memory safety and encapsulation, mutability, immutability of data structure. These are components that make the analysis, the privacy analysis is easier, and also the contribution, checking the correctness of contribution easier. In addition, we want some general form of data type and type safety, because we want to make sure that the different components stitch together without creating any problem. And for this, in the choice that we committed to is to use a combination of the Rust programming language, which is a low-level programming language which provides some of this feature, with some additional binding with Python and R. So the main idea is that we want to use Rust for the core library so that we can guarantee the correctness of the different component and we still have a good efficiency. But at the same time, we want, for ease of contribution, we want to have the possibility that contributor can contribute in Python and R. Now, I will briefly sketch how to use the library and how to contribute to the library, and then I will conclude. So to use the library, mainly a user need to determine which data set they want to use, the type, what are the components that they need, the kind of privacy notion they want to use, and the granularity. And then they can select some interactive measurement from the library and then present queries to the queryable that is created by the measurement. This is the basic usage, but of course, user can also contribute new components to this design. Now, to use the library, also some exposure of the underlying system is needed, like data access model, what are the capabilities that we have, and then also some kind of interface. For the contribution to the library, what we expect is that there are different kinds of contribution, from the new measurement or transformation combining existing component, which should come with an automated verifiability proof, to new type of atomic measurement or transformation, which instead need to be provided by user with proof of correctness. And for all of these, we will have different way of betting and agreement on the contribution. What we have so far is what we show you is a framework that support many different data type, privacy measure, and transformations. And what we don't have yet, but hopefully in the future we will have, is some more advanced feature of differential privacy, like privacy odometers or mechanisms based on local sensitivity, or support for randomized or interactive transformation. I ran out of time, and let me conclude by just saying again, what we try to give you is an idea of the different component of the library, and some of the practical consideration on how we plan to implement the library. And tomorrow we will have a breakout session on this. You're all welcome to come with your question and sharing your thoughts about this design. Thank you.
Thanks, guys. We have a question that just came up from Adam Smith. What, if any, is the intended scope of measurements? Is there any inherent limitation on the type of differential privacy algorithm that fits the framework?
Yeah, I mentioned some of the limitation. For instance, I went a bit fast on this slide. So some of the limitation are here in this last bullet point. For instance, at the moment, we don't deal with local sensitivity, but we expect that the framework itself could deal with it by adding more attributes to the different measurement and transformation, and make sure that we capture the notion of local sensitivity, and then we can use some of the standard tool like smooth sensitivity to deal with this. So there are some limitations, but we don't think our limitation of the general design is just we wanted to design a basic core and then go from there.
Right. So software can't do everything, not only in measurement, but in general. So what are the applications or types of differential privacy that we're sort of explicitly not attacking now?
So for the kind of differential privacy we want to address, I think the framework is general enough to address all the differential privacy related measures. So like I was saying before, approximate DP, NEDP, and so on. Maybe one thing that the framework is not yet designed for is reasoning explicitly about different adversarial models. So there are variations of differential privacy, like computational differential privacy, where there is some assumption about the computational power of the adversary. And these are notions that we don't support yet. Again, we hope in the future to be able to deal with them, but so far we don't address them.
Right. One more from Murat Kantarsioglu, whose name is definitely not pronounced that way. Will there be any support for privacy budget allocation in the programming framework for complex tasks?
Sorry, can you say again the question?
Will there be any support for privacy budget allocation for allocating epsilon in the programming framework for complex tasks?
Yes, so the idea is that, yes, there will be support for complex privacy budget management. So the idea of interactive measurement and generalizing to relation, these two ideas come exactly from the need of giving flexibility for the management of the budget. So yes, there will be.